Hey folks, Bill Armstrong here. The next thing we kind of look at is it's more work with the inverse trig functions. And next up you'll be seeing something about these things called cancellation equations. And I thought, I'd give a little bit of meaning behind these so-called cancellation equations. First off, you have the sine of inverse sine square root 3 over 2. Now what you will see is that this thing that they're calling a cancellation equation, that this will equal the square root of 3 over 2. Hence they're saying the sine and inverse sine, since they're inverse functions, they, quote, cancel out. Now let's think about the reason why this is true. First off, square root 3 over 2, that is a number between -1 and 1. So it's in the domain of the inverse sine function. It's a number between -1 and 1. If we didn't even know this cancellation equation, if we didn't know this at all, we could still do the problem. I mean, we can just simply do it. Inverse sine of square root 3 over 2. Remember, inverse sine is, its job is angle finder. It's to find an angle on the right half of the unit circle, from -pi over 2 to pi over 2. So inverse sine of square root 3 over 2, well, we know inverse sine of square root 3 over 2 is pi over 3. So this is the angle pi over 3. From the unit circle, what's the sine of pi over 3? It's square root 3 over 2. So you see, we didn't even need to know this cancellation equation to do the problem, but the reason why the cancellation equation works is because this number here is between -1 and 1. Now let's compare that to the sine of inverse sine of 5/2. I can tell you right now that this does not equal 5/2. And the reason why it does not equal 5/2 is because 5/2 is a number that is larger than 1. It's not between -1 and 1. So you would see that you can't apply a cancellation equation here. In fact, sine of inverse sine of 5/2, you can't do it. There is no angle that will satisfy inverse sine of 5/2. The angle doesn't exist. So this isn't even possible. Let's look at another one. Let's look at, make this part B, cosine of inverse cosine of 1/2. Alright, so here we are, inverse cosine. We know inverse cosine rips an angle off the top half of the unit circle from 0 to pi. That's the top half of the unit circle. Since that number is between -1 and 1, you would see that the cancellation equation tells you that this immediately simplifies to 1/2. And of course it immediately simplifies to 1/2. Because inverse cosine of 1/2, that's finding an angle on the top half of the unit circle. That angle happens to be pi over 3. So this is really just saying, what's the cosine of pi over 3? Well, from the unit circle, we know the cosine of pi over 3 is 1/2. So that's a situation of where you would be seeing you can use a cancellation equation. But let's compare that to the cosine of inverse cosine of 3/2. Can we use this concept, this idea of a cancellation equation, to immediately simplify that down to 3/2? Absolutely not. That 3/2 is not between -1 and 1. There's no angle that's going to make this true. You can't do this. So don't even think, I put a big old X through that equal sign, don't even think that equals 3/2 because it doesn't. Let's look at another one. Alright, so we have inverse sine of sine pi over 3. You would be seeing that your cancellation equation, because sine and inverse sine are inverse functions of each other, that this immediately reduces down to pi over 3. Now let's think about why. Pi over 3 is an angle in quadrant 1. That is on the right half of the unit circle. Inverse sine picks up an angle, it looks for an angle on the right half of the unit circle. So again, just like I was showing you, you should know that the sine of pi over 3 is square root 3 over 2. What's the inverse sine of square root 3 over 2? Well, it's pi over 3. So there's an example of, again, where the cancellation equation idea would work. Now let's compare that to the inverse sine of sine 5 pi over 3. This will not equal 5 pi over 3. This does not, big X through it, equal 5 pi over 3. Now let's think of the reason why. 5 pi over 3 is not between negative pi over 2 and pi over 2. Remember, inverse sine is looking for an angle from negative pi over 2 to pi over 2. 5 pi over 3 isn't between negative pi over 2 and pi over 2. But we could still do this problem. We could still try to determine what inverse sine of sine 5 pi over 3 is, because from the unit circle we do know what the sine of 5 pi over 3 is. The sine of 5 pi over 3, let's see, that is negative square root 3 over 2. So inverse sine of negative square root 3 over 2, well, that's negative pi over 3. So be careful in trying to use or to apply these cancellation equations. Let's do one more. Inverse cosine of cosine 5 pi over 6. So here we are, 5 pi over 6. That is an angle. If you look at the top half of the unit circle, 0 to pi, 5 pi over 6 is out there in quadrant 2, so it is between 0 and pi. Inverse cosine, its job is to find an angle between 0 and pi, so your cancellation equation would immediately tell you that this simplifies to 5 pi over 6. And again, if you just didn't know that cancellation equation, you could say, well, the cosine of 5 pi over 6 is negative square root 3 over 2. Inverse cosine of negative square root 3 over 2, yep, that's 5 pi over 6. But let's compare that to the inverse cosine of cosine 7 pi over 6. Okay, 7 pi over 6 is not between 0 and pi. It is not on the top half of the unit circle. It's down there in quadrant 3. So this will not, big X, it does not equal 7 pi over 6. But we can still just do this problem. I mean, if we just kind of take it a step at a time, cosine of 7 pi over 6. The cosine of 7 pi over 6, that's negative square root 3 over 2. Inverse cosine of negative square root 3 over 2, well, that is 5 pi over 6. So that's a little bit of a meaning behind these cancellation equations. All right, next up I thought we'd do a couple of examples of determining exact values of trig and inverse trig, just kind of all mixed in together. So the first one I have here is the sine of inverse cosine of 1/2. Just take it a step at a time. Work your way from inside out. Determine first what is the inverse cosine of 1/2. Inverse cosine, finding an angle on the top half of the unit circle. So inverse cosine of 1/2, well, that's pi over 3. So inverse cosine of 1/2 is pi over 3. What's the sine of pi over 3? Square root 3 over 2. So that is the exact value of sine of inverse cosine of 1/2. Notice how everything keeps coming back to this unit circle. The more proficient you are with the unit circle, the better your life is in trig. Let's look what I have up here for b. The secant of inverse sine square root 3 over 2. Well, we know inverse sine is finding an angle on the right half of the unit circle, and we should know that the inverse sine of square root 3 over 2 is pi over 3. So inverse sine of square root 3 over 2 is pi over 3. What is the secant of pi over 3? Well, honestly, I don't know what that is off the top of my head. I don't know what the secant of pi over 3 is off the top of my head, but here's what I do know. I do know what the cosine of pi over 3 is. I know that the cosine of pi over 3 is 1/2. So since I know the cosine of pi over 3 is 1/2, I know the secant of pi over 3 is the reciprocal of 1/2, which is 2. So the exact value of secant of inverse sine square root 3 over 2 is 2. And I used my knowledge of the unit circle and that the cosine of pi over 3 was 1/2 to determine the secant of pi over 3 was 2. Okay, the last one I have up here is to find the tangent of inverse cosine negative 1/2. Again, inverse cosine, angle on the top half of the unit circle, and I know inverse cosine of negative 1/2 is 2 pi over 3. So now I have to find the tangent of 2 pi over 3. I do not know the tangent of 2 pi over 3 off the top of my head. But the unit circle tells me what the sine of 2 pi over 3 is and what the cosine of 2 pi over 3 is. I know the sine of 2 pi over 3 is square root 3 over 2. I know the cosine of 2 pi over 3 is negative 1/2. So the tangent of 2 pi over 3 is sine over the cosine. It's using an old quotient identity. And then that reduces, takes square root 3 over 2 divided by negative 1/2. That reduces down to negative square root 3. So the exact value of tangent inverse cosine of negative 1/2, well, that's negative square root 3. So that's 3 quick examples of finding exact values of some sines and cosines and inverse functions and secants and tangents. Basically, all this came back to a friendly application of our unit circle and knowing our unit circle. All right, next example. This looks kind of similar to the 3 examples we just did, except there's one difference. I have a 2/3 in here. I don't have one of those convenient, one of those friendly points that I know on the unit circle. I don't have a square root 3 over 2 there, or a 1/2, or a square root 2 over 2. I have a 2/3. It's like, well, I have to do a little bit more work here. And the first thing that I'm going to focus on is the purpose of inverse sine is to find an angle. I know there is an angle, and I'll call it theta. I know there's an angle theta that exists on the right half of the unit circle, because it's inverse sine. I know there's an angle that exists that angle is inverse sine of 2/3. Notice, I call this like admitting. I know there's an angle that exists, but I don't know what that angle is off the top of my head. Notice that by making this admission, I have taken this problem and in essence, I have turned it into finding cosine theta. That's theta. Inverse sine 2/3 is theta. Well, hey, theta equals inverse sine of 2/3. Remember what that really means. That really means that sine of theta is 2/3. And now we're going to go back to identities. I cannot impress upon you enough how important it is to know your identities, your basic trig identities. Knowing the unit circle and knowing basic trig identities makes everything so much nicer, especially later on in future math classes. Whenever I know sine, and I do, I know sine theta is 2/3, I can immediately get cosine by using the Pythagorean identity, cosine squared theta plus sine squared theta equals 1. I can just immediately use this identity. I know sine of theta is 2/3, so I just substitute 2/3 in here for sine of theta. So I have cosine squared plus 2/3 squared equals 1. 2/3 squared is a 4/9. Subtract 4/9 from both sides, and I get cosine squared. Let's see, 1 minus 4/9, that's 5/9. And then taking the square root of both sides, I get cosine theta is plus or minus the square root 5/3. So how do I know what the answer is here? Is it the positive square root 5/3 or is it the negative square root 5/3? Well, think about this just a little bit. This equation here, theta equals inverse sine of 2/3. We know inverse sine is finding an angle off the right half of the unit circle. So right there we know theta is living in quadrant 1 or quadrant 4. But since this equation really means sine of theta is 2/3, that's a positive value. So I can narrow it down even more. This equation tells me my angle theta is in quadrants 1 or 4. Now this equation tells me without a doubt that angle theta has to be in quadrant 1. Because in quadrant 4, sine isn't positive. Sine is negative in quadrant 4. Now remember, all 6 trig functions are positive for any angle that terminates in quadrant 1. And because of that, I now know that I'm going to use the positive square root 5/3. So I know my answer here, the exact value of cosine of inverse sine of 2/3, that exact value is square root 5/3. Okay, folks, just a couple more examples to look at. I'm going to come back to something that's maybe a little more friendly. It's off the unit circle. Inverse sine of cosine negative pi/6. A couple of ways to do this problem. You could use your even and odd identities, or you could just simply use the unit circle. In other words, cosine of negative pi/6. I know negative pi/6 is an angle that has a clockwise rotation. And so if I know my unit circle, if I know it really well, I know that cosine of negative pi/6, I know that is square root 3/2. Inverse sine square root 3/2, that's finding an angle off the right half of the unit circle, pi/3. So the exact value of inverse sine cosine negative pi/6 is pi/3. Check this one out. This is a little slicker, if you will. The cosecant of inverse sine of 4/7. Alright, so I don't know where that is exactly on the unit circle, where this 4/7 is exactly on the unit circle. But it's going to look similar to part C of the last example that I did. In other words, I don't know what this angle is, but I do know it's an angle on the right half of the unit circle. Admit to yourself there is an angle that is equal to the inverse sine of 4/7. And it's on the right half of the unit circle. Now remember, this really means that the sine of theta is equal to 4/7. That's what it really means. So look at what we have here. Our original question by making this note that theta equals inverse sine of 4/7, you've turned this into an angle theta, so you've turned the original problem into cosecant theta. This is turned into cosecant theta. But if you know that the sine of theta is 4/7, thanks to the reciprocal identities, you immediately know that the cosecant has to be 7/4. So the exact value of cosecant inverse sine of 4/7 is 7/4. And that's it for that example.